So under D block elements, let us discuss now magnetic properties. Magnetic properties. Most of the D block elements exhibit paramagnetic property. Most of the D block elements and their compounds exhibit paramagnetic property. Why they exhibit paramagnetic property? It is due to presence of unpaired electrons in d orbitals. It is due to presence of unpaired electrons in d orbital. You take any transition metal or D block metal and their compounds, at least they are carrying single unpaired electron. Therefore, most of the D block elements and their compounds exhibiting paramagnetic property. If you consider a D0 electronic configuration or a D10 electronic configuration, D0 electronic configuration or D10 electronic configuration, they are not carrying any unpaired electron. Therefore, they are found to be diamagnetic. They are found to be diamagnetic in nature. We come across different types of magnetic properties. Different types of magnetic properties. The first property we can say paramagnetic property. Paramagnetic substance, let me say. Paramagnetic substance. Second one, diamagnetic substance. Diamagnetic substance. And third one, let me say ferromagnetic substance. Ferromagnetic substance. And next one, antiferromagnetic substance. Antiferromagnetic substance. Antiferromagnetic substance. So paramagnetic substance, diamagnetic substance, ferromagnetic substance, antiferromagnetic substance, and one more substance we come across, ferrimagnetic substance. Ferrimagnetic substance. Like this, different magnetic substances are there. You know well this particular paramagnetic substance. Paramagnetic substance. The substance which is attracted by the magnet. The substance which is attracted by the magnet, we call it as what? Paramagnetic substance. A paramagnetic substance generally carrying unpaired electron. Generally carrying unpaired electron. Whichever the substance carrying unpaired electron that is attracted by the magnet, such a substance we call it as what? Paramagnetic substance. Coming to diamagnetic substance. The substance which is generally repelled by the magnet. The substance which is generally repelled by the magnet, we call it as diamagnetic substance. Diamagnetic substance. Diamagnetic substance generally carrying paired arrangement of electrons. Paired arrangement of electron. Therefore, that particular substance is repelled by the magnet. Such a substance we call it what? Diamagnetic substance. Why? A paramagnetic substance is attracted. You see, if you are taking one unpaired electron in there, generally a unpaired electron always tries to make its spin 0. Its spin 0. Therefore, a unpaired electron carrying what? Plus of spin or minus of spin. To make its spin 0, it is moving toward the magnet to make the north pole and south pole of this particular magnet. One will be plus of, the other one will be minus of. Therefore, the plus of electron which is carrying plus of electron that is moving toward the magnet to make it spin 0. Therefore, this particular paramagnetic substance is attracted toward the magnet. Next, coming to diamagnetic substance. Why a diamagnetic substance is repelled by the magnet? See, when spin is 0, then it should not show any response. Generally, according to the number of unpaired electrons and the paired arrangement of electrons is there. According to number of electrons and pairing of electrons, we cannot say it is the diamagnetic. Now, a diamagnetic substance, whenever a diamagnetic substance is put in the magnetic field, there will be some induced paramagnetic moments are developed. These paramagnetic moments are working in opposite direction to the field of the magnet. Therefore, a diamagnetic substance is repelled by the magnet. What I am saying, when a diamagnetic substance is put in the magnetic field, there will be some induced temporary paramagnetic moments are generated. These paramagnetic moments working in opposite direction to the field of the magnet. Therefore, that particular substance is repelled by the magnet. Next, the effect of diamagnetic moment is less than paramagnetic moment. See, paramagnetic moment is a permanent one. It is there in the substance. But diamagnetic moment, what I said, it is induced by the field of the magnet. Therefore, it is induced, temporary and small. Because of this particular reason, since it is an induced magnetic moment, the diamagnetic effect is less than paramagnetic effect. Diamagnetic effect is less than paramagnetic effect because diamagnetic effect is a induced effect, but paramagnetic effect is permanent one. It is there in the substance. Next, coming to ferromagnetic substance. Ferromagnetic substance. The substance which is exhibiting greater paramagnetic moment than expected from the number of unpaired electron. The number of unpaired electron. Once you consider a substance you take which is carrying 3 unpaired electrons. This particular substance is carrying 3 unpaired electrons. Once it is carrying 3 unpaired electrons, you can expect theoretically a magnetic moment of 3.8. For example, I am giving 3.8 Bohr magnetons of magnetic moment it is exhibiting. But experimentally proved to be this particular substance is exhibiting greater than the expected. Now it is exhibiting 4.3 Bohr magnetons of magnetic moments, imagine. So the substance which is exhibiting greater paramagnetic moment than expected from the number of unpaired electrons. Such a substance we call it what? Ferromagnetic substance. Why a ferromagnetic substance is exhibiting greater paramagnetic moment? Because in a ferromagnetic substance, the paramagnetic centers are very near to each other. The paramagnetic centers are very near to each other. Once paramagnetic centers are very near to each other, alignment of their magnetic fields are possible. Alignment of their magnetic fields are possible. Means their magnetic fields are aligning together, working in the same direction. Working in the same direction of the field of the magnet. Therefore, that particular substance all together working in the same direction. Therefore, that particular substance is exhibiting greater paramagnetic moment than expected. Such a substance we call it what? Ferromagnetic substance. What are the examples under ferromagnetic substances? Now we can take most of the iron, cobalt, nickel. Most of the iron, cobalt, nickel and their compounds are generally exhibiting ferromagnetic property. Ferromagnetic property. In this ferromagnetic substances, the paramagnetic vectors or the magnetic vectors are in this way they are working. So all are working in the same direction in the field of the magnet. So the paramagnetic vectors of a ferromagnetic substance working this way. We can how to show this particular ferromagnetic substance. The vectors of paramagnetic lines are working in the same direction. Coming to antiferromagnetic substance. The substance which is exhibiting lesser paramagnetic moment than expected from the number of unpaired electrons. Look here, it is carrying 4 unpaired electrons. Once 4 unpaired electrons are there, it has to exhibit a paramagnetic moment of what you can expect 4.8. 4.8 Bohr magnetons of magnetic moment. But it is not exhibiting 4.8, it is only exhibiting 3.9, imagine. Then such a substance we call it what? Antiferromagnetic substance. The substance which is exhibiting lesser paramagnetic moment than expected. Such a substance we call it what? Antiferromagnetic substance. Antiferromagnetic substance. Why a substance is actually acting as antiferro substance? Whenever paramagnetic centers are away from each other. Once paramagnetic centers are away from each other, alignment in the same direction is not easy. Therefore, they may act opposite to the field of the magnet. So, some of the paramagnetic moments of this particular substance acting opposite to the field of the magnet. Therefore, that particular substance is exhibiting antiferro property. So, in antiferro property, the paramagnetic centers are away from each other. In a ferro substance, the paramagnetic centers are near to each other. Once they are near, aligning in the same direction. Once they are away from each other, alignment is not possible. Therefore, this particular substance is actually exhibiting antiferro substance. Antiferro substance exhibiting antiferro property. Next, ferrimagnetic substance. Ferrimagnetic substance. In some of the substances, In some of the substances, the magnetic vectors, the lines of magnetic vectors which are working in the direction of the field of the magnet and which are working opposite to the field of the magnet, once they are not equal, then that particular substance exhibiting slight paramagnetic moment, such a substance we call it what? Ferrimagnetic substance. Ferrimagnetic substance. In ferrimagnetic substance, the magnetic moment vectors, some I am writing like this, some I am writing opposite to each other. Some are like this and some are opposite to each other. These two are actually opposite to each other. These two are actually working in the same direction. Such a substance what to call ferrimagnetic substance. So, ferromagnetic substance exhibiting greater paramagnetic moment than expected. Antiferro exhibiting lesser paramagnetic moment than expected. Ferrimagnetic substance exhibiting slight paramagnetic moment. Such a substance what to call ferrimagnetic substance. Like this, ferromagnetic, antiferromagnetic substance and ferrimagnetic substance. Like this, different types of magnetic substances are there. Next we discuss what is Curie temperature and Néel temperature. We know now what are paramagnetic substances: paramagnetic, diamagnetic, ferrimagnetic and antiferrimagnetic substances. In addition to that, ferrimagnetic, antiferro and again ferrimagnetic substance. Let us see now total paramagnetic moment of any substance. Total paramagnetic moment of any substance. Total paramagnetic property. Total paramagnetic property of any substance equal to spin angular moment plus orbital angular moment. Spin angular moment plus orbital angular moment. Spin angular moment plus orbital angular moment. Total paramagnetic property of any substance dependent on two factors. One is spin angular moment and orbital angular moment. What is this spin angular moment and orbital angular moment? Consider an electron is actually revolving around the nucleus. Electron revolving around the nucleus, you consider. Once revolving, this particular electron is actually spinning on its own axis. Spinning on its own axis, developing a particular magnetic moment, what you call spin angular moment. While revolving itself, it is actually spinning on its own axis and again revolving around the nucleus. Once it is revolving around the nucleus in a particular orbit, again it is developing one more magnetic moment. While revolving in the orbit, developing particular magnetic moment, what you call orbital angular moment. One is spinning on its own axis, developing a particular magnetic moment, spin angular moment. Next, revolving around the nucleus in a particular orbit, one more magnetic moment is developed, that is known as what? Orbital angular moment. These two moments together only we call total paramagnetic moment of that particular substance. Total paramagnetic moment of that particular substance. Therefore, spin angular moment plus orbital angular moment. This we can also show by a equation nu s plus L. Here S stands for spin angular moment and L stands for orbital angular moment. The equation for this nu s plus L is equal to under root of 4s into s plus 1 plus L into L plus 1. L into L plus 1. This stands for orbital angular moment. This stands for spin angular moment. This stands for spin angular moment. This stands for orbital angular moment. Now, in D block elements, especially in 3D series, this orbital angular moment is completely quenched by the ligand fields. Completely quenched by the ligand fields. In other way, quenching means cancelled by the ligand fields. Why? In D block elements, what I am saying, especially in 3D series, the orbital angular moment is completely quenched by the ligand fields because the d orbitals are there in the penultimate shell near to the ligand fields. What do you understand by this? Look the board. Now let us talk about 3D series. 3D series means fourth period. Let me write 4 shells. 1, 2, 3, 4. Then electronic configuration, let me say it is 4s2. For 3D series, it is actually 3D. Now, this particular ligand is here, ligand it is. ligand is here very near to the d orbital. Therefore, the field strength of this particular ligand is affecting the orbital angular moment of electron in the d orbitals. So, in d block elements, especially in 3D series, the orbital angular moment is completely quenched or cancelled by the ligand fields, because the ligands are there in the d orbitals are there in the penultimate shell, that is, it is near to the ligand fields. Therefore, ligand field is affecting the orbital angular moment of electrons in d orbital. Therefore, half of the equation is sufficient to calculate the total paramagnetic moment, especially in 3D series. Therefore, we can write now mu effective. Mu effective is equal to only half of the equation I am taking here, that is under root of 4s into s plus 1. Under root of 4s into s plus 1 is enough. The same equation generally you also know, you use one more equation in addition to that. Mu effective is also equal to under root of n into n plus 2. N into n plus 2. One more equation you use under root of n into n plus 2. One more equation is also there to calculate this particular only spin angular moment. G into under root of s into s plus 1. S into s plus 1 also you can use. Here G stands for gyromagnetic ratio. Gyromagnetic ratio, its value is 2. So, by using either of the equations, we can calculate the total paramagnetic moment. Whether you are using the first equation or the second equation or third equation, all are one and same. For applying all the three equations, you will be getting only one value. Suppose one electron is there, unpaired electron. Then use the first equation or the second equation, third equation, you will be getting only 1.7 bm. 1.7 bm. So, either of the equations are having same meaning and same value they are giving. Only wherever you are applying s, wherever you write s, consider as the spin. Wherever you are writing n, consider the number of unpaired electrons. N stands for number of unpaired electron, S stands for spin of the electron. Accordingly, you can calculate the magnetic moment of any given number of unpaired electron. Now, once we know the number of unpaired electrons in any metal or any substance, we can easily say its magnetic moment. It's a magnetic moment. I will write a small table, try to understand this. What I am writing, look the board. Number of unpaired electrons. Number of unpaired electrons and magnetic moment. Magnetic moment. Magnetic moment in BMs. Magnetic moment in BMs. Magnetic moment in BMs. Now, one unpaired electron, 2, 3, 4, 5. This is what number of unpaired electrons, imagine. Then magnetic moment comes to be. Magnetic moment comes to be. If one electron is there, you can take 1.72 2 bm, you can take 1.72 2 bm. If two unpaired electrons are there, you can take 2.8 through 8 to 3, you can consider 2.8 to 3. And 3 unpaired electrons are there, you can take 3.83 to 4 magnetons you can take. Once you are taking 4.87 to 5 you can take. If 5 is there, 5.9 to 6 you can take. Like this, roughly you can say the magnetic moment. What you can understand by this particular table, if one unpaired electron is there, 1.8 to take roughly, 1.8, 2, 2.8, 3, 3.8, 4, 4.8, 5, 5.8, like that you can take the magnetic moment. In any substance, if unpaired electrons are known, we can say its magnetic moment that 1, 1.8, 2, 2.8, 3, 3.8, 4, 4.8, 5, 5.8, like that you can say the magnetic moment of any substance once you know the number of unpaired electrons. Next, these magnetic moments are generally measured in Bohr magnetons. What to say? Bohr magnetons, BMs. See, one BM equal to EH by 4 pi mc. One BM is equal to EH by 4 pi mc. Once a question appeared, define BM. You need not write any definition for this. Simply you can write 1 BM is equal to EH by 4 pi mc. E stands for electronic charge, H stands for Planck's constant, M stands for mass of the electron, and C stands for velocity of light. If you substitute all these values, that will give the value for 1 bm. So the magnetic moments measured in Bohr magnetons, 1 bm is equal to Eh by 4 pi mc. Eh by 4 pi mc. Generally, magnetic moments are measured by using a balance. Magnetic moments are generally measured by using a balance. What do you call this particular balance? This particular balance is Guy balance, you see. Guy balance. The magnetic moments are generally measured by using Guy balance. Guy balance is actually experimental setup is like this for the Guy balance. This is what two magnetic poles will be there. Two magnetic poles will be there. One in north pole, the south pole. In between these two, a small glass tube is actually hanging. This is actually connected to a digital weighing machine. Suppose you have taken a certain substance in this. This particular substance, you don't know what is the nature of this particular substance. It may be a paramagnetic or it may be a diamagnetic, but you don't know what is the nature of the substance. Then consider 1 milligram of the substance you have taken. What you have taken? 1 milligram. Now once it is paramagnetic, once you put on the instrument, then its weight is increasing. Say why it is increasing? It is attracted by the magnetic field, therefore its weight is increased. After putting on the instrument, once its weight is increased by 1.5 milligrams to say, then you can say that it is attracted. Therefore, you can consider that particular substance is what? Paramagnetic. Once its weight is decreasing, suppose this 1 milligram has become 0.5 milligram, then what you can say? It is repelled by the magnetic field. Therefore, any unknown substance, once you are putting in the magnetic balance due to magnetic field, it may be its weight is increasing or decreasing. Once its weight is increasing, say it's paramagnetic substance. Once its weight is decreasing, say it's what? Diamagnetic substance. Accordingly, increase or decrease in weight, the unknown substance you can say paramagnetic or diamagnetic. Increase in the weight, you can easily calculate. Based on the increase in the weight, you can calculate number of unpaired electrons in that particular substance. This is the way we do calculate the magnetic moment. Based on the magnetic moment, we can say what number of unpaired electrons are there in a given particular substance. This is about magnetic balance and how we calculate the magnetic moment of a given substance. How a question appear on this particular magnetic properties. In a compound of cobalt, the magnetic moment is 6 bm. What will be the oxidation state of cobalt? Oxidation state of cobalt. In a compound of cobalt, the magnetic moment is 6 bm. What will be the oxidation state of cobalt? Now A is given as what? +2 take, and B +3, C +4, D none. Such a question appeared in the examination. 6 bm is given. 6 bm means what I given? If it is carrying 5 unpaired electrons, its magnetic moment is 5.9 to 6, I said. You have to check it in which oxidation number cobalt is carrying 5 unpaired electrons. Yesterday I explained. Now you can take this particular cobalt 27 D7S2. Now you consider +2 oxidation state. +2 means it is what? D7. How many unpaired electrons in the D7? Only 3 unpaired electrons. It is not our answer. Next, coming to 3. In +3 oxidation state, 2 electrons from S, 1 electron from D, then it is D6 configuration. D6 means what? 4 unpaired electron. It is also not our answer. We require 5 unpaired electron. Then consider +4 oxidation state, then it will become what? D5. Then 5 unpaired electron. Answer is what? +4. So questions are appearing like this. So they will give the magnetic moment. They will put a question, what is the oxidation number? What is the oxidation number? Then you have to check it according to the given magnetic moment. First you have to check number of unpaired electrons. Accordingly, which oxidation number is correct answer? According to this particular question, the answer is what? +4. In +4, it is carrying D5 configuration, 5 unpaired electron. Then magnetic moment is 5.926. So answer is what? C. Next, magnetic properties were completed. Next, let us see color properties of D block elements. Color properties. Color properties. See, most of the D block elements and their compounds. Most of the D block elements and their compounds exhibit color. It is due to presence of unpaired electrons in d orbital. It is due to presence of unpaired electrons in d orbitals or incompletely filled d orbital. Presence of unpaired electrons in d orbitals or incompletely filled d orbital. Second reason, you can say it is due to d to d electronic transitions. D to D electronic transition. What is this D to D electronic transition? This particular transition you can also say according to crystal field theory T to G to EG electronic transition. This you can also write as what T to G to EG electronic transitions. T to G to EG electronic transitions, you can see. What is this? According to crystal field theory, you might be knowing this 5 d orbitals under the influence of any ligand. Under the influence of any ligand, consider a CN minus, a aqua ligand, a amine ligand, you can take any ligand. Under the influence of this particular ligand, the 5 d orbitals splitting into different energy levels. The 5 d orbitals splitting into different energy levels. Higher energy level we consider what EG, and lower energy level we consider what T to Z. This is what T to Z and EG. Now you consider a D3 electronic configuration. After the splitting, the electrons are entering into lower energy levels. After splitting, the electrons are entering into lower energy level. Next, the energy difference between these two energy levels is very less. That what to represent delta O. Delta stands for energy difference. O stands for octahedral geometry. The splitting of orbitals in octahedral geometry is like this, T to Z and EZ. Now, the energy difference between these two energy levels is very less. It is more or less equal to visible region of light. Now, color from this particular visible region of light is absorbed. Imagine X color is absorbed. Then electron from lower energy level is excited to higher energy level. Electron from lower energy level is excited to higher energy level. You know well, this electron in the higher energy level is less stable. Once it is entered to the higher energy level, again it comes back to the same lower energy level. While de-excitation, absorbed energy is actually transmitted. Whatever the color it is transmitting, that will be the color of the compound. That will be the color of the compound. What is this DT transition? Yes, both are d orbitals only. Lower energy level is d orbital, higher energy level is d orbital. This particular we are calling it as what? D to D electronic transition or T to G to EG electronic transition. This is the reason for the most of the D block elements and their compounds exhibiting color. Next, the color properties dependent on various factors. What are the factors influencing the color properties of D block elements? The factors influencing the color properties of D block elements. Let us see that. The color properties are influenced by the color properties are influenced by color properties are influenced by the first one, number of unpaired electrons, number of unpaired electrons, number of unpaired electrons in d orbitals, number of unpaired electrons in d orbitals, or you can say number of incompletely filled number of incompletely filled d orbital. The color properties of d block elements much more dependent on the various factors. The first factor is number of unpaired electrons in d orbitals or number of incompletely filled d orbitals. Second factor, nature of the ligands. Second factor, nature of the ligands. Second factor, nature of the ligands. Now you consider Cu, I am writing 3 examples here. Cu H2O taken 4 times, copper tetraco complex, then this you substitute with a amine ligand, then Cu NS3 taken 4 times, this is again plus 2, and you can also take Cl minus Cu Cl4, Cu Cl4 minus 2. This is aqua complex, amine complex, chloro complex. Now this is actually light blue in color. This is light blue, this is dark blue in color, dark blue, but this is actually green in color, dark blue and green in color. What do you understand by this? If you are changing the ligand, the color is also changing. Aqua complex light blue and amine complex dark blue and chloro complex green. As the ligand you are changing, color is also changing. Therefore, color property dependent on nature of the ligand. Coming to next one, geometry. The color property is also influenced by geometry. Consider simply a nickel plus 2 ion. Nickel plus 2 ion. Remember, nickel plus 2 ion can form 3 types of complexes. It may be a octahedral complex, which I am writing as octahedral complex, and it may be a square planar complex. Let me say tetrahedral complex. Nickel plus 2 D8 only. Nickel plus 2 D8 electronic configuration, right? In nickel plus 2 D8, it is forming 3 complexes. 3 are having 3 different geometries. In all these geometries, in all these complexes, what is the metal ion present? Nickel plus 2. What is the configuration? D8 only. In all these, metal ion is same and configuration is same. But once their geometry different, and these 3 are definitely exhibiting 3 different color. Consider first one, for example, let me say X color. Second one definitely Y color. Third one definitely Z color. So only the difference in the geometry makes they are exhibiting different colors. One is X, Y and Z. Like this, the color property dependent on 3 factors. One is number of unpaired electrons d orbitals or incompletely filled d orbitals, and nature of the ligands, and also geometry. These are the factors influencing the color property of d block elements and their compounds. Next, look here, there is a relationship between absorbed and transmitted colors. There is a relationship between absorbed and transmitted colors. Let me write a small table: absorbed and transmitted, absorbed and transmitted colors. Now consider X color is absorbed, Y color is transmitted. Once Y color is absorbed, definitely it is transmitting X color only. There is a relationship between absorbed and transmitted color. X is absorbed, Y is transmitted. Once Y is absorbed, X is transmitted. Consider, suppose blue color is absorbed, only orange is transmitted. If orange is absorbed, you can easily say blue is transmitted. The pairs of colors, either XY you take or blue and orange, orange and blue. This particular blue and orange, the pairs of colors, what we call them as complementary colors. Complementary colors we call this particular, the pairs of absorbed and transmitted colors, we call them as what? Complementary colors. Now let me show a table. Entire visible region we take, what color is actually absorbed, what color is actually transmitted. What are the complementary colors among this particular visible region of light? Visible region of light. Let me make a table here, then you can easily understand what color is absorbed, what color is transmitted. Now let me say here, first I will write VIBGR. VIBGYOR. Here I write UV. Here I am writing what? IR. Let me number these particular colors. You see, it is your infrared, red, orange, yellow, yellow green, a combined color is there. Then you say green, and again blue green and blue. This is what indigo and violet. I am numbering for convenience sake to write the absorbed colors: infrared, red, orange, yellow, yellow green, green, blue, indigo, violet. I made this particular numbering to make the all absorbed color. It is only simply our convenience how to make this particular absorbed colors. The same numbering I am following the order. You see, infrared, red, orange, yellow, green, then you take green, yellow, green, then you can say blue green and blue, indigo, and you take violet, then let me say UV. These are the order of absorbed colors you take. Then we have to make the complementary colors for this. Complementary colors for this. Now I am numbering like this: 1, 2, 3, 4. Let me see: blue, green, blue, indigo, and violet. Blue, green, blue, indigo, and violet. Now see this particular infrared. You know this particular infrared is what? Invisible. Look at here. Once invisible is absorbed, invisible only transmitted. Therefore, once infrared is absorbed, it will be colorless. Infrared, colorless. Next you take red, orange, yellow, green. These particular 4 numbers that is considered. If orange, it is blue, green is transmitted. Red. If next orange, it will be what? Blue is transmitted. Yellow, then it will be indigo. Indigo is transmitted. And yellow green, this will be violet. For this particular green, a separate color is there. Then you can take it is what? Pink. Green is absorbed, pink is transmitted. Once you make this particular half of the table, remaining half you can make. Come on, say easily you can make it. Now blue green, it will be red. Then blue, you can easily say it is what? Orange. And indigo, you can say yellow. And next violet, it is yellow green. Then UV, you can simply say it is again colorless. UV is again invisible. Once invisible is absorbed, invisible is only transmitted. So according to this table, we can understand that what color is absorbed, what color is transmitted, in what way these are actually complementary to each other. But question never appears if orange is absorbed, what is actually transmitted. But what actually you are understanding from this particular table is, when a color from longer wavelength region is absorbed, color from shorter wavelength region is transmitted, and vice versa. Look at here, red is absorbed. Red is what here? Longer wavelength region. Once longer wavelength region is absorbed, shorter wavelength region, blue green. What is blue green is transmitted. Longer is absorbed, shorter is transmitted. Suppose shorter is absorbed, longer is transmitted. That we are understanding from this particular table. What we can conclude? When a color from shorter wavelength is absorbed, a color from longer wavelength region is transmitted, and vice versa. Shorter is absorbed, longer is transmitted. Longer is absorbed, shorter is transmitted. That is the concept we are understanding from this particular table. So this is complementary colors, and it's the table. Let us see how a question appears on this particular color properties. Now, which of the following is colored? Which of the following is colored? Consider A, it is what? CuCl, B, Cu2Cl2, C, and CdCl2, D. Let us take CuCl2. This is the question up here. Then you have to say, according to our generalization, wherever no unpaired electron, D0 configuration is there, D10 configuration is there, that particular compound is found to be colorless. Now we consider CuCl. Cu is actually +1. +1 means what? D10. Therefore it is colorless. Coming to Cu2Cl2, same oxidation number. This is what again? Cu +1. Still it is what? D10. And CdCl2, you know, Cd is also +2. Still it is what? D10 configuration. Therefore colorless. In the case of CuCl2, you can consider Cu +2. This is what actually D9. Therefore CuCl2 only exhibit color, as CuCl2 carrying what? D9 configuration. One unpaired electron is there. Then the excitation and de-excitation is possible. Absorption and emission is possible. Therefore only CuCl2 is exhibiting color, remaining all are colorless. This is the way questions appear in the examination. One more important point is there in this particular color properties. Now let me explain what is that important point here. What I generalized actually, any configuration, D0 configuration, D10 configuration, these are actually colorless. These are actually colorless. Now we consider D0 or D10, you can take scandium +3 and titanium +4 you take. And D10 configurations you can consider copper +1, simply zinc +2 you take. These are what? D0 configuration, these are D10 configuration. They are colorless, no doubt. But one very important thing is there in the case of KMnO4 you take, potassium permanganate. Consider one more point, K2Cr2O7. K2Cr2O7. What is the oxidation number of manganese in this? Well known to you. Manganese is what? +7. What is the oxidation number of chromium? Well known to you. It is what? +6. What is the electronic configuration of Mn +7? D0 configuration. D0 configuration. So what is the electronic configuration of manganese? 25 means D5S2. How many electrons are there in the valence and penultimate shell D and S? 7 electrons. It is losing all the 7 electrons. It is becoming what? Equal to 0. Then chromium +6. What is the configuration? D5S1. Losing all the 6 electrons. Then it is again D0 configuration. See, KMnO4 and K2Cr2O7, both of these are carrying D0 configurations. What we said, if D0 configuration is there, they should not exhibit in color. But I hope you know well, KMnO4 and K2Cr2O7 exhibiting color. You might have seen in the laboratory, KMnO4 is dark purple in the color, dark purple in color, and K2Cr2O7 dark orange in color. Both of these are exhibiting color even though D0 configuration, no unpaired electron. This is due to charge transfer phenomenon. It's very important. In most of the exams, this particular question is frequently appearing. The KMnO4 and K2Cr2O7, even though D0 configuration exhibiting color, this is due to charge transfer phenomenon. It's a very important term to remember. Charge transfer phenomenon. Charge transfer phenomenon. It's very important to remember. KMnO4 and K2Cr2O7, even though D0 configuration exhibit color, this is due to charge transfer phenomenon. Next, let us see the next heading, catalytic properties we will discuss. Catalytic properties. Catalytic properties. Catalytic properties. See, most of the D block elements and their compound generally we use as what? Catalysts. Why D block elements only preferred in industrial catalysts or in other chemical reactions we are using many times, the many reactions we are using this particular catalyst only, either D block metals or their compounds. Why we prefer to use these, why these are acting as what? Best catalysts. It is due to variable oxidation states to take. Variable oxidation states or variable valencies. variable valencies. Variable oxygen states or variable valencies. It is also due to presence of unpaired electrons in d orbitals, unpaired electrons in d orbitals or incompletely filled d orbital. Variable oxygen states are variable valencies, or it is due to unpaired electrons and incompletely filled d orbitals. Then you can take in the finely divided state, in the finely powdered state, these are having greater atomic surfaces. In the finely powdered state, these are having greater atomic surfaces, easily adsorb the reactants. Now we consider A and B plus catalyst, let me say D block. D block. A and B reactants in presence of catalyst D block element, and because of greater atomic surfaces, this is actually easily adsorbing this particular reactant and facilitate the reaction to take place. Facilitate the reaction to take place. What you are getting? AB catalyst. This is unstable intermediate you are getting. Unstable intermediate. Unstable intermediate you are getting. Ultimately, it is decomposing. You are getting what? C product. Again, you are getting catalyst. Due to these particular reasons. What reasons? Variable oxygen states, variable valencies, unpaired electrons, incompletely filled d orbitals, finely powdered state, they are having greater atomic surfaces, adsorb the reactants and form a unstable intermediate and facilitate the reaction to take place. Because of these reasons, most of the D block elements and their compounds act as best catalysts. Best catalysts. Just few catalysts and their industrial importance. I will make a table so that you can remember. These catalysts are also very important. In most of the entrance exams, these are frequently appearing. Very few I mention on the board now. Catalyst and importance of the catalyst. Catalyst and its importance. Catalyst and its importance. Let me take the first one, Ziegler-Natta catalyst. Ziegler-Natta. Ziegler-Natta catalyst. It's very important. It's very important. It is actually appearing in most of the entrance exams. Now you take, it is actually a mixture of titanium tetrachloride plus aluminum alkyls. Titanium tetrachloride and aluminum alkyls. It is a mixture of titanium tetrachloride and aluminum alkyl. What is actually importance of this particular catalyst? It is actually used for low temperature polymerization of ethylene to polythene. Ethylene to polythene. Low temperature polymerization of ethylene to polythene. Very important catalyst. You might be knowing this particular V2O5. V2O5. It is commercial manufacture of what? Sulfuric acid. Sulfuric acid by contact process. Sulfuric acid by contact process. This is the particular catalyst is used. So, Ziegler-Natta catalyst V2O5. MnO2. MnO2 is the catalyst used for the decomposition of KClO3. Decomposition of KClO3 for the preparation of oxygen. Now you consider FeCl3. FeCl3 used for this manufacture of CCl4 from CS2 and Cl2. CS2 and Cl2. These are some important catalysts and their commercial importance. This is about catalytic properties of these elements. Next we see the complex formation and formation of interstitial compounds. Complex formation. Complex formation. Most of the D block elements highly capable of forming complex compounds. Why these are highly capable of forming complex compound? It is again variable valencies, or you can take variable oxidation states. variable valencies or variable oxygen states, presence of incompletely filled d orbitals, presence of incompletely filled d orbitals or unpaired electrons in d orbitals. Next, smaller size of their cations, greater charge density, smaller size of their cations and greater charge density. Consider this particular ferric ion. Consider ferric ion Fe plus 3. Fe plus 3 is very small in size, possess greater positive charge density. Positive charge density. It can easily show a electrostatic force on the ligand. Electrostatic force on the ligand easily. Therefore, variable valencies, variable oxygen states, unpaired electrons in d orbitals, incompletely filled d orbitals, smaller size of their cations and greater charge densities. These are the reasons for why this particular d block elements easily form complex compound. You might be knowing complex compounds. Let me write one or two. K4FeCN taken 6. Potassium ferrocyanide we call. And let us take K3FeCN taken 6. What to call? Potassium ferricyanide. It is ferricyanide, iron plus 3, ferrocyanide, iron plus 2. Like this, most of the d block elements highly capable of forming complex compound due to these reasons. Next, let me discuss the interstitial compounds or alloys. Interstitial compounds or alloys. Interstitial compounds or alloys. What are these interstitial compounds or alloys? You take a transition metallic lattice. Transition metallic lattice. In any lattice you take or solid you take, the atoms are tightly packed like this. Tightly packed like this. Yes, you are clearly observing on the board, whatever the way they are tightly packed, you are clearly observing there is interatomic spaces. Interatomic spaces. These interatomic spaces, we call them as interstitious. Interstitious, interatomic spaces. These interatomic spaces occupied by smaller atoms like it may be hydrogen, boron, carbon, nitrogen, oxygen. The interatomic spaces or interstitious are occupied by smaller atoms like hydrogen, boron, carbon, nitrogen, producing special type of compound. Special type of compounds known as interstitial compounds or alloys. Now, the transition metallic hydrides, borides, carbides, nitrides, oxides. The transition metallic hydrides, borides, carbides, nitrides, oxides all are coming under interstitial compounds. Interstitial compounds. Next, why d block elements are highly capable of forming these interstitial compounds? Due to more or less same reasons, presence of or variable valencies. Presence of variable valencies or variable oxidation states, variable valencies, variable oxidation states, and again due to incompletely filled d orbitals, and unpaired electrons. These are the reasons for this particular d block elements are easily forming this interstitial compound. Variable valencies, variable oxidation states, unpaired electrons, incompletely filled d orbitals. Next, this particular interstitial compounds are exhibiting some special properties. What are the properties exhibited by these interstitial compounds? Interstitial compounds. Now, properties of interstitial compound. First one, their chemical properties more or less identical to chemical properties of parent metal. Chemical properties of parent metal. So, chemical properties of these compounds are more or less identical to parent metal. Next, physical properties we talk about. Physical properties, they are differing from parent metal. Physically they are actually different, but chemical properties are more or less identical to this particular parent metal. Next, look at here, these are actually very hard substances. Very hard, their melting points are very high. Very hard, their melting points are very high. Their melting points are even more than parent metal, even more than parent metals. Next, these are, remember, non-stoichiometric compounds. These are non-stoichiometric. These are non-stoichiometric. They are not following any valency rules. They are non-stoichiometric, not following any valency rules. Valency rules. Next, these are non-stoichiometric and not following any valency rules. The best examples, and these are actually good electrical conductors. These are also acting as what? Good electrical conductors. Under these best examples, you can take cast iron. Cast iron and steels. Almost all the steels and cast iron, you can take the examples under interstitial compounds or alloys. Interstitial compounds or alloys. Next we discuss the electrode potentials. Electrode potentials. Look here, copper and mercury are having positive reduction potentials. Positive reduction potentials. Positive reduction potential. Any element which is having greater reduction potential, that is positive reduction potential, they cannot easily liberate hydrogen from dilute acids. Dilute acids. This particular copper and mercury cannot liberate easily hydrogen from dilute acids like dilute HCl or any other dilute acid. These cannot easily act as what? Reducing it. Excluding these particular two elements, remaining most of the D block elements having negative reduction potentials. Negative reduction potentials. Once negative reduction potential is there, lower reduction potentials, these will be above hydrogen in the electrochemical series. Once negative reduction potential is there, then these are found to be above the hydrogen in the electrochemical series. The elements which are having negative reduction potentials, they are above hydrogen in the electrochemical series. They can easily liberate hydrogen gas from dilute acid. This particular remaining all the elements easily liberate hydrogen gas from dilute acids. Now we consider chromium, manganese, yes, chromium, manganese, iron, cobalt, nickel. Chromium, manganese, iron, cobalt, nickel we consider. These are having what? Negative reduction potential. Negative reduction potential. What I said, the metal or element which is having negative reduction potential values, they have to liberate hydrogen gas easily from the dilute acid. Even though these are having negative reduction potential, they are not easily liberating hydrogen gas. They are not easily liberating hydrogen gas. This is due to formation of protective oxide layer on the surface of these metals. What I said, negative reduction potential is there. They have to liberate hydrogen gas easily, but they are not easily liberating hydrogen as we are expecting. This is due to what factor? These are easily forming a protective oxide layer on the surface. Chromium easily generating a oxide layer Cr2O3, Mn2O3, Fe2O3, CO2O3, Ni2O3. Because of this particular reason, even though they are having negative reduction potential values, they are not easily liberating hydrogen gas from dilute acids. Dilute acids. Next we see the shapes of d orbitals and metallic lattices of d block elements. Metallic lattices. Metallic lattices. See, these metallic lattices, generally any solid or a metal possessing generally three metallic lattices. Either it may be HCP metallic lattice, well known to you, BCC metallic lattice, or it may be FCC metallic lattice. HCP means hexagonal close packing, BCC body centered cubic lattice, and FCC face centered cubic lattice. Generally any solid or the metal possessing either of the three metallic lattices. Questions appearing on this metallic lattices. What is the metallic lattice possessed by zirconium? What is the metallic lattice possessed by zinc? Such questions are appearing in the different entrance exam. Therefore, it is better to remember the metallic lattice of this particular D block element. Yes, it is difficult to remember all the 30 elements and their metallic lattices. By let us say all the 3D, 4D, 5D, we classify these particular elements and try to remember in easy way this particular metallic lattices. I am writing now 3D, 4D, 5D, 3 series. I will classify in easy way this particular metallic lattices. Now you consider 3D series to take scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. 3D series. Come to 4D series. Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. 4D series to take. Next you know this 5D series. Take lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, Au, Hg. Now these are 3D, 4D, 5D elements. Now the first two series, the first two vertical columns are having a metallic lattice of HCP. Metallic lattice of HCP. First two vertical columns HCP. Second two vertical columns having a metallic lattice of BCC. Metallic lattice of BCC. Third two vertical columns having a metallic lattice of again HCP. But one thing you have to remember, this manganese metallic lattice is not clearly known. Next, iron is not having in this HCP, but with the exception it is having a BCC metallic lattice. Next, coming to remaining three vertical columns having CCP or FCC. Both are one and same, CCP or FCC. In this, all 9 elements except this particular cobalt is having HCP. Remaining all are having FCC or CCP. Last, zinc is having a metallic lattice of HCP. Cadmium is having a metallic lattice of again HCP. These are the metallic lattices. And mercury is liquid, therefore it is not having a particular metallic lattice. So remembering all the 30 elements and their metallic lattice is little difficult. Therefore I made it little easy to remember. Most of the D block elements are having HCP metallic lattice. Look the board. Next, easy to remember. First two vertical columns HCP, second two BCC, third two HCP, but one or two exceptions. And next 3 vertical columns all are having CCP or FCC, and cobalt is HCP, zinc HCP and cadmium HCP. Like this, in easy way you can remember the metallic lattices of this particular element. How the question appear? Which of the following element is having HCP metallic lattice? Such questions are appearing. So that if you could able to remember in this way, easily can answer in the entrance exam any type of question appearing on this metallic lattices. Next we see shapes of d orbitals. Well known to you, it is well covered in your first year and there, but still in a detailed discussion we require the shapes of d orbitals. Now in the d subshell there is 5 d orbitals. The d subshell there is 5 d orbitals. The d subshell there is 5 d orbitals, well known to you. This is what dxy, dxz and dyz. You can take dx square minus y square and dz square. So dxy, dxz, yz and dx square minus y square and dz square. Out of this particular 5 d orbitals, first 3 dxy, xz, yz, we classify this particular as what? T to the set of orbital. T to the set of orbital. Remaining 2 we call it as what? EZ set of orbital. EZ set of orbital. Can you say what is the difference between T to Z and EZ, two sets of orbital? Remember, in the case of T to Z set of orbitals, the orbitals are, the lobes are oriented in between the axis. The lobes are oriented in between the axis. These are known as what? Non-axial orbitals. non-axial orbitals. These, the lobes are actually oriented along the axis. These are generally known as what? Axial orbital. These are axial orbitals. These are non-axial orbital. Let us see the shapes of this particular d orbital. Once you talk about dxy, this is actually oriented between x and y. This is actually oriented in between x and y, plus plus and minus minus. This is what to say dxy orbital. And dxz you take, it is oriented in between x and z. Oriented in between x and z. This is plus plus and again minus minus. This can take xz. Then yz oriented in between y and z. This is what yz orbital, which is oriented in between y and z. So let us say this y and z. You are clearly observing these are what I said, non-axial. These particular orbitals are oriented in between the axis. These are what? Non-axial. These are oriented along the axis. Consider dx square minus y square. Oriented along x axis and y axis. It is oriented along x and y. This is considered what? Dx square minus y square. Let me say wave functions also I am putting plus plus and minus. This is x square minus y square. Next can take dz square orbital. This is what xz. This is oriented along only z axis. This is dz square orbital. This is plus plus and minus minus. This is dz square orbital. Now what you are looking? These are oriented along the axis, axial orbital. Oriented in between the axis, non-axial orbital. Moreover, I put plus plus and minus minus. Imagine these are not the charges. These particular signs, whatever I put, these are only wave functions. Wave functions. Next, you are clearly observing in these orbitals, the opposite lobes are carrying identical wave functions. Identical wave functions. We can easily cut these particular orbitals into two equal halves. This particular carrying opposite lobe same wave function, we can cut into equal halves. Therefore, they are symmetric. Therefore, this particular all the d orbitals we can call them as what? Geode. Geode means what do you understand? Geode means symmetric. Geode means symmetric orbitals. Symmetric. Next, all the d orbitals. This particular dz square orbital is dumbbell in shape. Dumbbell in shape, and also its shape also we can call it as baby method. Baby method in shape. Baby method in shape. Dumbbell in shape or baby method. Remaining all the orbitals, we are clearly looking, these are what? Double dumbbell in shape. Among the d orbitals, dz square orbital is dumbbell in shape. Remaining all are actually double dumbbell in shape. All the d orbitals, opposite lobes are carrying identical wave functions. They are symmetric. Therefore, they are known as what? Geode orbital. These are all geode orbital. This is about this particular d orbital. And one more point also we can say, this particular dz square orbital. This particular dz square orbital is a combination of dz square orbital is a combination of dx square minus z square, and it is actually dy square minus z square. It is a combination of dx square minus z square and dy square minus z square. This particular dz square is the combination of both of these particular orbitals. This is about shapes of d orbitals.